Hi, everyone. Welcome to the virtual Spark AI Summit 2020. I'm Mike Diaz, and along with me is Luke Heinrich. I work as a data engineer, and Luke works as a data analyst. We both work at Atlassian. And today we are going to talk about how we build understanding out of incomplete and biased data sets using machine learning and Databricks. But first, I'm going to introduce you to Atlassian as a company and the data landscape that we work with. At Atlassian, we believe that behind every great human achievement, there is a team. From medicine and space travel to disaster response and pizza deliveries, our products help teams all over the planet to advance humanity through the power of software. Our mission is to help to unleash the potential of every team. To achieve this mission, we build work collaboration tools to help our customers to achieve their potential and do great things. Some of our most popular products are Jira, Confluence, Bitbucket, Trello, Statspage, and Upstream. We give our customers the deployment options that are more suitable to them. For some customers that are ready for our cloud offering, where we manage everything for them, we have the cloud offering. But for those that are not ready yet, we also have an on-premise solution where the customers can install our products in their own environment. In both cases, we have to make sure that we are building great products and meeting our customers' expectations and needs. And among several things, there's one particular thing that's very important to build great products, and that thing is called product analytics. Product analytics help us understand how users navigate our products and engage with our features, all with the aim of building better products. So product analytics let us understand our users and validate hypotheses to create the best possible products and features. And the way that we work is that we instrumented our products, both cloud and on-premise, to capture user actions that we can use to generate insight about the product usage. In our cloud products, the analytics data flows through a real-time streaming pipeline. And in our on-premise products, we accumulate the analytics data and send it once a day. But it's very important to say that we never capture anything sensitive, like personal identifiable information or user-generated content. Everything is secure and anonymized. And in order to make the data accessible by data workers, we process it using Spark structured streaming technology and in both stream and batch pipelines, which land the data in the Atlassian data lake. We store this data as Spark tables where Atlassians can access this data and correlate with other data sources to generate insights to help our teams to go and build better products. More broadly, at Atlassian, the Atlassian data lake is very heterogeneous in terms of processing and ingestion. In addition to product analytics, we also have several other data sources like internal databases and system integrations. The data can flow as a stream, as batch, via AWS Kinesis, Kafka, and other technologies as well. And we also have other file formats like CSV and Org stored in the data lake. But no matter how the processing looks like, all the data ends landing on S3, and they are mapped as tables via GlueMat store, where all the data lake tables are registered and organized by namespaces. These tables are accessed via SQL using Databricks and AWS Athena. We are also very flexible in terms of visualization tools. So data analysts and data scientists can use their favorite tools to create their insights, like Databricks notebooks, Tableau, Redash, Amplitude, and so on, and share their discovery with product managers that can use this information to make more data-driven decisions. As I've been mentioning, everything data-related at Atlassian is AWS-based. We rely on S3, Glue, Athena, and our Databricks account is also running on AWS. Our data lake is petabyte scale and keeps growing at a rate of 100 terabytes per month. We also have 2,000 internal users of the data lake per month. And we have more than 200 data workers which their primary job is to deal with data, like data engineers, data analysts, data scientists, and so on. But let's back to product analytics. Although we have a lot of data, we don't have all the data all the time. Consider this case. In our cloud option, we have the complete products analytics dataset, so we can fully correlate with other datasets, like license, for example. Having the complete dataset gives us a lot of confidence about the insight extracted from this dataset. Having the complete analytics dataset isn't always the case. Our product analysts are opt-in, and some of our on-premise customers keep their products behind their firewall, making it impossible to share analytics data with us. So from our perspective, we know the customer purchased a product license, but we don't know how they use the product. That is an incomplete and biased dataset that leads to consequences that are going to be explained by my mate, Luke Harry. Over to you, mate.
Awesome. Thanks, Mike, and hi, everybody. It's great to be here, and I hope you're staying safe in these crazy times. I want to introduce you to the problems that come up with biased and incomplete data by running through a few examples, where hopefully by the end of them, you have an appreciation for why data, like the one we have here, can become pretty messy when trying to do analytics in practice and analytics at scale. So let's start off with a simple question. A product manager comes up to you and asks how many customers are using a feature that they've just shipped. This is the bread and butter of building understanding about product use and making data-informed decisions. Now, for this example, I want to simplify the problem by imagining that in reality, we only have two customer groups. Group A on the left, of which 10% of customers use the feature, and Group B on the right, where 90% use the feature. That's a very big swing between groups, and let's say that each group comprises half of the true customer base. So if we were answering this question and had access to the complete and true data set of product use, we'd say that 50% of customers use a feature, the average between them. And that's something that's easier to see when you have the full picture. Just create a 1 or 0 based on whether the customer uses the feature and take the average across your base. It's a very quick query. But let's add some bias into this scenario and say that due to the opt-in nature of product analytics, the red group is twice as likely to send analytics to us. In this case, the data that we receive is comprised of 2/3 of customers from the red group and 1/3 of customers from the yellow, as represented by the bars on the slide. Whilst this is not the true mix of customers in reality, it does represent the mix that we're querying in our product analytics. And a direct query on this data set will produce that just 37% of customers use the feature, as this set is now biased to the red group, who use the feature a lot less. Now, is this what's going on in practice? Well, no, but it is what we see on the other end, based on who's kindly decided to send us product analytics to work with. And how about if we said instead that we had a larger bias of 3 times, but this time towards the yellow group, who use a feature a lot more? In this case, we directly query an answer that 70% of customers use the feature, well above the answers of the last 2. As you can see, it can be a bit of a problem because the reality is that directly querying biased data gives an answer that is both a function of how many customers actually use the feature and how that feature use varies within the biases of your data set that you're working with. For this example, our analytics data could create a raw response anywhere between 10% and 90%, depending on how extreme the bias is towards either group. With that in mind, you have to be wary of whether your data is providing much value or whether it's just providing an undue confidence in a certain number. And you might be thinking that the bias I've just described is extreme, but here is an actual bias that exists in the product analytics of one of our tools, where larger licenses, as defined by how many users they're licensed for, are almost half as likely to opt in and send us analytics compared to smaller ones. Now, if you're analyzing a feature that appeals to those trying to manage and deploy our products at scale, this particular bias can become very impactful. You might be thinking of some of the techniques you could use or judgment you'd apply in dealing with the bias and creating an answer for that last example. But that one was isolated. And the reality is that over time, we have many analysts that create many answers across many products. It's never just a one-off deep dive into the data and forget about it thereafter. So let's move on to our next example of how many users are impacted by a given platform change, something that affects many of our products. In this example, let's say that we have 3 analysts, Jim, Jane, and John, who each work on products A, B, and C, respectively. Let's start off with Jim. Now, Jim, after receiving this question about how many users are impacted, runs his query and sees that 15 users are affected in our product analytics data. The true amount of users affected, remembering that our product analytics is just a sample, is actually 45. And Jim doesn't do anything to the number he receives, expecting everyone else to do the same, and reports back to the business that 15 users are impacted for product A. And now let's move on to Jane. So Jane goes and runs a similar query for her product and finds that 10 users are affected. Again, because our data is a sample, the true number is actually 30. Now Jane goes and extrapolates based on a simple logic of how many people are phoning home. So for this example, let's say that we have 50% of customers phoning home. So Jane doubles the number to make that 50% look like 100% and reports that 20 users are impacted for product B. And lastly for John, John sees 8 users and also does an extrapolation, but tries to control for that size bias we talked about earlier. He upweights large licenses and generates an estimate that 25 users are impacted for product C. Now, if you're following along, you'll see that based on what's truly going on for our customers, product A has the largest impact from the platform change, but reported the lowest amount of users impacted. And conversely, John, despite being the closest to reality with his estimate and objectively doing the best job, reported the highest impact for product C, when in fact it has the lowest impact. This example is one where the incomplete data has given a completely wrong view of the impact of the platform change and had a detrimental impact on decision-making. Not necessarily because one method applied consistently would give the wrong answer, but because people were using different ones. And now, this might come across as a bit extreme because if this question was asked in practice, you'd see a much tighter collaboration between analysts. But imagine that Jane is doing her analysis 2 months after everybody else. Jim's analysis was a quick and unrelated one that a product manager has gone and taken the numbers from. And John could be in a completely different department. When moving fast and at scale, ensuring past experiments and insights are leveraged, examples like this can become very possible. And so hopefully from those examples where things have fallen down a bit, you agree that bias and incomplete data sets can cause a few problems in practice. Really, that has the potential to become a bit of a Wild West if everyone goes and does their own thing. Which leads us to the bigger topic of this speech, and that is how we try and solve this by providing self-serve estimation. And why estimation? Well, because every answer we create with our data is an estimation of what we think is going on in reality. And it's a gritty kind of estimation. It's not an A/B test where you randomly assign cohorts to different experiences and estimate the uplift and error according to known formulas, or a truly random sample where you might have 10% of the population, but a random 10%, one that you can reliably infer from and provide confidence intervals of how wrong you might be. Instead, we know that our sample of product analytics is biased. We have the statistics to prove it well beyond reasonable doubt. And it's impossible for us to know what we don't know, to truly know what reality looks like. So really, we're always just trying to estimate. And estimation is studied a fair bit in statistics under the random setting, having a lot of defined properties that are desirable. Things like unbiasedness, that your number will be accurate on average, or consistency, where your estimate gets more and more precise as your data volume increases, or efficiency, where you're using the best metric to estimate some unknown quantity. But in practice, there are more things that you want when building estimates at scale to help a business make decisions. Things like auditability, that you can look at the numbers and see or reproduce the calculations that got them. Consistency, in the second sense now, that one analyst is using the same methodology as another, so decision makers are able to compare apples with apples. And best practice, that ideally each estimate makes best efforts to control for biases in the data. Understanding that stakeholders are on board and trust the methodology, having some appreciation for where it has limitations. And the last one I mentioned, but I could go on, is accessibility. The analysts up and down the spectrum of technical and programming abilities all have the ability to use a methodology. And now you still want the ones on the left. They're very important, but those on the right are a tad more gritty. And when things go wrong in these, they're sometimes felt pretty hard in practice. So to build out something that satisfies these properties, and we'll reflect on them later on, we provide self-serve estimation to anyone using our product analytics. So what does that mean? We'll progressively get through the detail, but how it works at a high level is that for all licenses that are not sending us analytics, we provide similarity scores between them and the licenses that do send analytics to us. A license that we don't know about effectively distributes itself over the pool of known licenses, saying that I'm X% similar to that one and Y% similar to another. Now, these scores allow the user to quickly create a predicted environment for those who don't send us analytics data, allowing them to work with any metric as if they had the full picture. From a practical perspective, it looks something like this, where the analyst first goes and creates a data set of licenses and metrics, where some, in this case license A, do not send us data and do not have a known value for the measure they're looking at. The second step is to detach on the similarity scores we provide through a simple join, where here A is considered 5% similar to B, 8% to C, and so forth. And then the user can estimate the unknowns through a product of the similarity score and the known metrics. So for A, it's estimated as 5% of the value for B, plus 8% of the value for C, and so forth, ultimately creating a predicted value for the unknown license. By now having attached this estimated column, the analyst can calculate metrics, effectively ignoring that they're working with a sample of the data, such as estimating the average of this metric across the whole customer base, not just the ones that we're observing. Now let's go down even further, because I've described similarity scores without any guidance on how we even generate them. Our first step to create these similarity scores is to build a predictive model to product use based on attributes that we know for all licenses, irrespective of whether they send us product analytics or not. To give some examples of this, think of things like how long they've owned the product, how many seats they have for their license, how they own our various other products, all the way to things like how they engage with our ecosystem and extensibility. Now, just like more traditional examples, imagine that those who don't send us product analytics are our validation set, and we're trying to optimize our model on the known data to ultimately predict on them. Now, this is taking the assumption that the better we can describe the known data, the better we can describe the unknown. Now, in order to create similarity scores rather than just have a dot predict capability, we build a random forest to the problem I've just described. We use a random forest as we're able to capture its internal tree structure to define similarity. This is because, ignoring the bagging aspect, a random forest predicts using a weighted average of the training data that lands in each terminal node. That is, predicting an unknown example is just created through a weighted average of the training data. And if you haven't made the link already, it's those weights in the weighted average that we use as our similarity scores. Now, they can be extracted with the formula on the slide, namely, similarity is a fraction of terminal nodes, two licenses landing together, normalized for how many other known examples are in that terminal node, and taken across all trees in the forest. And that random forest is great for us compared to other kernel or similarity methods because the supervised element provides feature selection in defining similarity, as opposed to other methods like k nearest neighbors, which treats all input variables equally. And the tree structure makes it simple, as we don't need to pre-process, normalize, or homogenize any of our features for a distance calculation. Now, once we have these weights or similarities, we dump those and the scored out model output into our data lake. These scores are available to all users to estimate any arbitrary metric. It can be what we trained onto, or maybe they'll be used to estimate usage of a given feature that it wasn't explicitly trained on. Sound familiar to the earlier example? This is because this is basically transfer of a trained model to a different response. And just like other circumstances you might have seen it used in, some responses do better at transferring to a certain situation than others. Accordingly, we have trained forests to additional responses, such as product co-use. Here, an important characteristic in defining similarity is whether a customer actually owns both products, something that might be uninteresting when just predicting generic usage or scale. Now we dump each model into our data lake, and the user is able to select which one they want to use for their estimation. And talking about users, diving into code next, I wanted to show the simplicity from a UX perspective to create estimates. This is in the context of the earlier example of 1, 2, 3, where you create your metric on known data, attach similarity, and then work out an estimated column to work with. Now at the top there, in the custom table expression, the user goes and defines their metrics on analytics data however they want. They own that section, and it can be broadly applied to whatever they're looking at. Now from there, they just join on the similarity tables and take the similarity weighted average of known examples. That is, some similarity multiplied by the metric within similar licenses. Now the true query does have other metadata like the model chosen and a date of the model score, but the crux of the code is that simple. In a few extra lines of SQL, they've gone from an observed data set to using a fairly complex and considered model to build an estimate for the full population, something that was sort of unavailable to them before. And we can go further, with next on the screen being the code on how the tree structure would be used in SQL to generate an estimate. I won't run through this directly, and sorry for maybe scaring you, but it's one of the blessings of doing this remotely that it's hopefully easy for you to pause or go back for the recording if you're interested. Now you might be wondering why a data worker might want the tree structure rather than just using similarity scores. And the answer is that known data is a bit of a simplification that can break down in more complex cases. To provide an example of this, our on-premise products have versions that the customer chooses to upgrade to or be on. And perhaps an analytics event was bugged for a given version, meaning that similarity for customers on those versions need to be dropped out in the calculation, as the analytics for them in this calculation is unfortunately meaningless and they're basically unknown. From a pipeline perspective, we start with our known input variables for all licenses sitting in our data lake. We run a daily scheduled Databricks notebook that scores all our models. Those models were built in another notebook and scored into MLflow that can be accessed by the daily scoring job. And we just use the random forest implementation in sklearn. Now the job populates model results back into the data lake as discussed earlier, with those tables now able to be combined with product analytics, allowing the data worker to quickly create estimates and largely forget they were ever working with a biased and incomplete data set. Fairly happy days. And before we move on to the next section, I want to come back to the properties we discussed earlier and see how this solution shapes up. So from an auditability perspective, we have our models built in Databricks notebooks and stored in MLflow for all the auditability that provides. And from a practical perspective, the analyst just needs to write they used our logic from that day and the calculation will flow. Consistency, it's absolutely so when multiple analysts are using our extrapolation logic rather than generating their own. For best practice, we can always tune our model more and more, but at this stage it's using many available attributes in a fine-tuned way to the known data, something that people couldn't easily replicate on the fly or build out within a SQL query. In understanding, it effectively lets analysts outsource that to us, where we've socialized the results to a wider on-premise business, meaning they need to spend less time explaining techniques and more time building insights. And lastly, for accessibility, any analyst just needs to use SQL. It's as much as it's helpful, they don't really need a comprehension of supervised learning or random forests or so forth to leverage this output. So hopefully you'll agree that it serves these properties pretty well. And now you've got a bit of a taste for scaling out estimation in an organization via the self-service. We want to make things a bit more tricky and run through subadditive metrics in this framework. Because everything we spoke about in the past falls down when metrics aren't affine or additive. What's a good example of a metric like this? Monthly active users, or as it's often known, MAU. The distinct count of people using a product set or a set of products, or maybe some functionality within them for a given window of time. So it might be DAO or WOW or basically anything else as well. Now, before I move on, I'd like to flag that all this estimation has a huge asterisk on it, and this definitely isn't something we report on externally. We stick to our cloud products for that, where it's known and reliable. And we do this estimation because our product teams in our on-premise business still want to try and understand this for the purpose of their decision-making, even when the estimate comes with a fairly hefty error bar and originally gave us a bit of a headache. Well, why the headache? Because it's a distinct count. And in Atlassian, our products work great together and users often interact with a lot of them. And so in this equation here, sticking with MAU, on the left you have a Jira instance with 14 monthly active users next to a Confluence instance with 11. And when you put them together, you calculate a MAU of 17. Only 3 of those users in the Confluence were not active users of Jira. And again, I'll stress that when you have the complete data set, this calculation is easy and reliable. Just grab your universe and do a count distinct. But what happens when we remove some data? Well, 14 plus question mark is unfortunately question mark. It all becomes unknown. And we can go even further, not knowing the value for the first license either. And for an analyst trying to create a distinct count estimate in this environment, they need to consider who in an unknown license isn't already captured in their known data. That is, they only need to add on the new users in the unknown license. And further, they need to repeat that for the other license, now also considering who they've latently added from the first one and making sure that they are excluded from the second one. As difficult as that already becomes, we're then back to square one with all of our problems. Because when people try and make their own approximations or assumptions or a distinct count, although they might be using our linear similarities for per instance or license estimation, they're adding their own flavor on top of it. And the math of consistency is that consistent plus inconsistent is still inconsistent. Maybe a little bit more than if the first part was also random and up to the discretion of the analyst, but it's still that original problem that we faced earlier. But what does a typical equation in this world look like? That is, what is 9 plus 10? Well, if we have a customer with 2 different products, like Jira and Confluence, in the same geography, it might be 11 when put together. There's a lot of co-use as our products work really nicely together. But what if it was the case of one of our multinational customers who have, say, a Jira license in the USA and maybe one in Sweden or somewhere in a completely different geography? In that case, none of the users might overlap at all, and 9 plus 10 is, as you'd normally say, 19. There's plenty of room for interpretation for how these calculations should be estimated, and we're left asking, how do we provide a similar framework to solving this problem of estimation at scale? And that's what we'll run through now. That even when things get tougher, estimation can still be made a lot easier for your organization. And I'll flag that in the interest of time and understanding, a lot of the technical details here will be in the slides, and I'll remain fairly high level in the speech. When starting off, we again use a predictive model, but this time for the distinct element of MAU or whatever the subadditive calculation is. This time, it's an iterative process where what we say is the MAU of a set of licenses is equal to the MAU of that set minus 1 license plus a fraction of the MAU in that license we excluded. So what does that mean? Well, maybe we have 2 licenses with 20 MAU together, and then there's a third that has 10 MAU, but when you put it all together, it's 25. So 20 plus 10 is 25. In that case, it's 20% plus 50% of that 10 MAU in order to make 25. And it's that 50%, or the fraction of the next license that we should include, that we go and predict. Because we have some data, we're actually able to build out a supervised model for this fraction, or the weight, based on characteristics about the set of licenses that we've already considered and the one that we're adding. Things like whether it's the same product, a different geography, relative sizes, and so on. And this model goes the whole way up from putting 2 instances together to maybe adding an 11th license to 10 that have already been considered. By using known or predicted MAU per license, using that pass method of generating it, we can then score this out to everyone and create a per customer MAU estimate. Start with the first, predict the weight for the second and add it in, then do the same for the third and so on, until all licenses for the customer are considered. And from this, we have the ability to estimate total MAU, not just MAU within a single license in isolation. And for this estimation framework, our next step is to allocate back the subadditive total to individual licenses, effectively creating an additive metric. Now we do this proportionally, and a simple example of what this means is, say I have 2 licenses, one with 10 users and one with 20. So the second one is double the first. But let's say that together they only have 24 MAU, not 30. Here we need to allocate that 24 back to the individual licenses. So in doing that, we say the first one is worth 8 and the second one is worth 16. So they're both scaled down by 20% and they sum up to 24. They're MAU together. Now, the large instance still has an allocation twice the size of the first, i.e. it's proportional to their amount when considered alone. Now, once that's done, we focus on how the known licenses predict the unknown. Because for all the estimation magic in predicting the unknown, what actually goes on is that we're just smartly scaling up known data in order to estimate the whole. That's all that we're doing. And now in that sense, if I'm a known license and there's two unknown licenses that have 50% similarity to me each, then everything I do is worth double when scaled out to the whole population. If another user in my license uses a feature, we estimate that two more did in the whole population. Or it expressed it, the license has an influence of 2. And that influence score, or 2 in the situation as described, is what we build out for each license in our estimation. And once we have those influence scores, they can be transferred quickly towards any active use calculation, such as a distinct count of users of a single feature only. It's the same way as we could before. Analogous to how we provide similarity scores for multiple responses to transfer from in the linear case, we provide influence scores for multiple windows, such as a single product window or all products together, or maybe just a single geography. This is because the allocated now methodology changes on what universe of licenses you look at. It shrinks the greater the universe is. But with those influence scores, it becomes really, really simple to build a distinct count estimate, as we'll now run through. And so back to this UX perspective in a bridge code. In this world, the top query again has a user-defined calculation of active users, and the join is a simple attachment of influence scores that they need to use to scale their estimate up. Now, you might be wondering why the earlier code snippets weren't as easy, and this is because it's a distinct count. Data workers can only work with the universe of licenses that were built for this calculation, rather than any arbitrary subset of, say, just these 10 licenses. The limitation here actually creates simplicity for its use, as we no longer have to account for any arbitrary situation. But hopefully you see that it's very easy to create estimates of active use, despite the complexity of the world that they're living in. Biased and incomplete data, plus trying to estimate a subadditive metric on top of it. I also won't go back to the earlier slides of properties, but thinking through some of those on the right, like consistency and accessibility, you'll find that this method satisfies them in the same way that it did before. So thanks for sticking with us this far, and we'll move into our summary and Q&A now. So we went fairly deep into the technical implementation of our estimation methodology, but I want to get back to the high-level crux of our problem and solution. Our on-premise product teams rely on a biased and incomplete data set of product use to help them better understand the customer and build better products. And we wanted to infer from that as best we can in a scaled manner. Through using accessible smarts, we've got a method for all data workers to create consistent and accurate estimations for the whole population, with the end result being quicker and more trustworthy insights back to the team. It's that simple. And before Q&A, I'll take this opportunity to remind you about providing feedback. We'd love it. Please be as candid as you like and can be. Feedback is a gift for us to try and improve. And otherwise, we'll be online for Q&A now. Apologies in advance if anything sounds a bit dopey, as I believe it'll be around 8 a.m. in Sydney and the coffee might have kicked in yet. But thanks a ton for attending. We both hope you got something out of it and you can make some connections to your own organization and the way it uses data. I'm sure you'll find something incomplete sitting around somewhere. Cheers again.